morning friends. We shall be continuing with our discussion on quantization. Last time we saw if the transfer function Hz is written as the ratio of two polynomials, then say for any one of them we can write the polynomial in this form. We can also write in the product form, where Z I will be the roots of this, the factors I varying from 1 to n. Okay. We saw the sensitivity delta Z I by delta A k with the parameter A k is Z I to the power n minus k divided by this product Z I minus Z j, where j equal to 1 to n, j not equal to I. Okay. Now, let us see the representation of a quad, a biquad say. You can have say the output is y n z to the power minus 1. Suppose the roots are complex, okay, minus r square, r square z to the power minus 1. For this, what are the possible values of the roots? You know, the roots are r cos theta and r sin theta for this. Okay. Now, this is the structure of just one factor, one quadratic factor. So, what should be the location of the roots? If we have say a 3-bit representation of these parameter values 0, 1, 2, 3, 4, 5, 6, 7, 8. So, this is 1, this is 7 by 8, this is 4 by 8, this is 1 by 8, 2 by 8 and so on. Okay. Similarly, 1, 2, 3, 4, 5, 6, 7, 8. So, what would be the values of r square? R square is this constant and this is 2r cos theta, and these are the things which are quantized. Okay. So, r square is quantized to any of these levels. So, r square will be 1 by 8, 2 by 8 and so on up to 7 by 8, okay, including 0. So, what would be the values of r? It will be 1 by root 8, 2 by root 8, that is half, and so on. Okay. If you check it, approximately 1 by root 8 is 1 by 2 root 2. So, approximately 0.35, 0.5, 0.61, 3 by 8, square root of that, then 4 by 8, so 1 by root 2, 0.7, then 0.79, these are approximate values, then 6 by 8 is root 3 by 2, okay. So, 0.866 and 7 by 8, so that is approximately root 8 0.875, So, approximately 0.94. Okay. So, if I take radius of these values 0.35, so it is somewhere here, this is 0.25, so somewhere here, then 0.5, then 0.6, so somewhere here, .7, sorry, this is 5, 0.6 should have been, 0.6 is somewhat here, sorry, this is not there. Anyway, like that 0.7 will be somewhere close to this, 0.79. So, like this you can plot, it will be somewhere here, then 0.86 and 0.94 you can plot it, 0.866 and 0.94. I am not plotting all of them. Then what will be the quantification of 2r cosine theta? 2 is a multiplier, of course. So, I can take even r cosine theta. So, they will be just 1 by 8, 2 by 8, 3 by 8, all right. And so on, 5 by 8, 6 by 8, 7 by 8. I have not drawn the other circles as yet. So, these are the possible values of r cosine thetas and so on. Okay. So, you will find in this zone they are rarefied, they are all compressed around this. These are the possible values the parameters can take with this structure, all right. If you increase the bit representation, that is, instead of say 2 to the power 3, if I have 2 to the power 4 or 2 to the power 5, 2 to the power 6, if it is an 8 bit number, then this will be partitioned much more closely, all right, and hence the distribution will appear more or less uniform. It will be still a little rarefied on the lower side and little compressed on the higher side, but you get more discrete values, and then I mean the discretization will be very, very close. There is another representation of the same quadratic form. This is very interesting. This is r cosine theta, this is z to the power minus 1, this is r sin theta, this is output yn, this is r cosine theta. This is minus r sin theta. This is xn. Okay. You try to find out the output and input relation, take it as an exercise. All right. Now, in this case, what would be the possible values of the parameters? They can be only r sin theta and r cosine theta. These are the constants, all right. these are the constants to be quantized. So, they look like (1 by 8, 2 by 8, 3 by 8, 4 by 8 and so on). If you draw circles, actually you need not draw all the circles, you will find these are the grid positions, is it not? R cosine theta can take only these possible values. Similarly, R sin theta can take only these possible values. So, it will be just a straight grid. It is bounded by this, that is all. So, these are the grid points. It is a uniform grid. Only thing, it does not exceed this value. And so on. Okay. Now, this is all about parameter quantization. Now, let us see the signal. When we quantize the signal, what is the kind of error that we get? We have a signal xn, and then sampler, and then you have quantizer. So, this is the quantized quantity x hat n, or sometimes we write x q n, quantized output. So, we are having the difference between these two will be the error, x hat n minus x n is the error. Now, any real number x we are expressing as some x m into minus b 0 plus b I 2 to the power minus I in the 2's complement form. In the 2's complement form, if I have the number b 0, b 1, b 2, etc., okay, then x is represented accurately by this if you can go up to an infinite number of bits. Okay. X m is any arbitrary scale factor. Now, in the 2's complement, the leftmost bit, this is representing the sign, okay, and rest of them are integer or fraction. We take it as fraction. Okay. So, between two numbers sorry, we take binary fraction point between two most significant digits. between 2 most significant bits. So, for b equal to 2, for the 2's complement, rather b equal to 3, okay, b equal to 2, the total number of bits is b plus 1 for the sign bit. So, b equal to 2, the 2's complement is like this. We write 3 by 4, 2 by 4, 1 by 4 and 0, and then 1 1 1 as minus 3 by 4, 1 1 0, minus half, 1 0 1, this is minus 1 by 4, minus 3 by 4, and 1 0 0 as minus 1. Okay. If you have a 3-bit word length, that is, if you have b is equal to 3, now let us write in 2's complement, 1's complement and simple sign magnitude. So, what do they represent? 0.111, the decimal point is here. I did not show, this is the decimal point. So, similarly, for 3 bits to represent the fraction and 1 bit here, so it will be b plus 1 is 4. So, this is a binary binary representation. This is the sign magnitude representation. This is 2's complement and this is 1's complement. So, 0.111 will represent 7 by 8, 7 by 8, 7 by 8. Okay. 0.110, similarly 6 by 8, 6 by 8, 6 by 8. So, like that, when it comes to okay, 0.01 will be 1 by 8, 1 by 8, 1 by 8. The change starts now. 0.000 will be 0, 0, 0. Then 1.000 will be 0 minus 1 minus 7 by 8. Okay. 1.001 will be minus 1 by 8 minus 7 by 8 minus 6 by 8. And lastly, if you continue like this, be 1.111, which will be minus 7 by 8 minus 1 by 8 and 0. Okay. If you remember, we discussed in 1's complement notation 0.000 is same as 1.111. It is like plus minus 0. Similarly, 0 here is 0.000. So, in general, we have, suppose we have A0, A1 up to AB, that is B number of bits. Total number of bits is B plus 1. then the number is in 2's complement is a0 minus a0 plus 2 to the power 0 plus a1 2 to the power minus 1 plus a2 2 to the power minus 2 and so on. Okay. So, for example, 1.110 will be minus 1, 2 to the power 0 means always 1, plus a1 is 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2. So, that gives me minus 1 by 8. Okay. After this it will appear somewhere in between. .111, is this coming all right? 1.110 is 1/4 and half, all right. So, how much is it? Minus 2 by 8, is that so? It should be 2 by 8, it will tally with the previous one. Now, suppose we have a signal varying from some plus magnitude to minus magnitude. So, we scale it by that factor xm and then we try to represent by this quantized variables. So, let me sketch it. Okay. So, this level is delta, this level is 2 delta, okay. This level is 3 delta, this is delta by 2, 3 delta by 2, 5 delta by 2, 7 delta by 2, and it continues. I can have 9 delta by 2 and so on. Okay. This is the variable x and this is a quantized variable x hat. Similarly, here this is minus delta, minus 2 delta, minus 3 delta, minus 4 delta. Okay. This is minus 3 delta by 2, this is minus delta by 2, minus 5 delta by 2, minus 7 delta by 2, minus 9 delta by 2. Okay. So, this is 0 1 1, I will show it here. This level is 0 1 1, 0 1 0, this level is 0 0 1, this is 0 0 0. Okay. Then this one is 1 1 1, 1 1 0, 1 0 1, 1 0 0. Okay. This is 2's complement. All right. If you take offset offset code, this will be just one less. On this side will be 111, 110, 101. This one will be 100. Similarly, this one you can fill up 011, then 010, 001 and 000. Okay. Suppose, okay, this is the range we call twice xm. So, the quantized, what the quantization level, that is delta, is twice xm divided by 2 to the power b plus 1. B plus 1 is the code length total. So, that will be xm 2 to the power minus b. This is the value of delta. X hat n is xm into xb hat n. If I call it xb hat, so this is basically scaled between plus minus 1, you can say, all right, and that has to be finally multiplied by this factor xm. So, that will give you the actual quantized value. Suppose we have a sinusoid. A sinusoidal signal. Varying between, say, plus minus 1. Two to 4 to 6, 2 to 4 to 6. Okay. Suppose we have something like this. Okay. Now, you may have quantization levels like this, say delta, okay, somewhere here, delta, 2 delta, 3 delta. I have chosen the lengths little shorter, delta, 2 delta and say 3 delta. Okay. These are the levels, say, and suppose the sampling time is t, 2t, 3t, 4t, 5t and so on. Okay. So, at this moment what we are sampling is this value. And what will that be represented as? 3 delta. So, this is the sample value. Sample value I will put as a cross. At 2t, our value is here, that is approximated as this quantity. At 3t, it is coming over here, and that is sampled as delta itself. at 4t it is this, it will be close to 0, and 5t it is here, it will be like this, and at 6t it is here, so it will be sampled as this. So, the values are like this. If I join, this sinusoid will appear as, say, previous to this I have not sampled, I have not shown you the sample value. If I start a sampling here, so it will be also like this. So, it will be a function like this, it will continue till the next instant, then it will come here, then it will be like this, it will be like this, then it will be like this. Similarly, if I sampled here, that will also be approximated here. If I take the next sample somewhere here, it will be like this, so it will be approximated here, and so on. So, you can see maybe somewhere close to 0. This will be the representation, that this red blocks, that will be the representation of the sinusoid. It will be changing if I change the sampling time. It will be approximating close to the sinusoid if I have more number of bits. Okay. So, that is why for a very correct representation you should have a large number of bits, and also you should have a very high sampling rate. If our sampling rate is high, then at least these blocks will not, this error will not continue for such a long time. So, error En is x hat n minus x n. So, if you have delta by 2 x n, 3 delta by 2, suppose x n is lying between delta by 2 and 3 delta by 2, between this point and this point. The actual signal is passing through this value, all right. So, this is the value of x. So, the error x hat n will be taken as delta, and minus delta by 2 so error is between plus minus delta by 2, is not, it can be it can vary only between these 2 points. So, the valid range is minus 9 delta by 2 to 7 delta by 2. You have seen it here, from minus 9 delta by 2 to 7 delta by 2. This is the range of variation of x. In general, it will be minus x m minus delta by 2 . plus xm minus delta by 2. Okay. So, this is xm minus delta by 2, that is minus xm minus delta by 2 and plus xm minus delta by 2. The whole thing has been shifted by delta by 2 on both sides. If xn is outside this range, for example, in the sinusoid we have chosen less number of steps. If it is outside this and if it is more, then this will not be, the error will be very large, error will not be restricted within this. Okay. Error is large, not within this limit. So, if you quantize and if you restrict your value of xn within this limit, then we can have a linear model for error. Additive noise can be representing the error. Okay. We can write xn plus En is equal to x hat n. Now, so this is known as additive noise. So, this is the model for the quantizer. Now, what will be the statistical representation of this error, the noise? We are making certain assumptions at this stage. About the property of this noise. En, the first assumption is En is stationary random process. It all depends on the signal. If the signal is varying, all right, then you can have a random process representation. Suppose it is a step function, then it does not change. It is not. So, that time you cannot have, that is an exception, but for the general signals it will be always changing. So, you can assume that the error is stationary and random. Error is stationary means it is restricted within minus delta by 2 to plus delta by 2, and it can vary within that with equal probability. So, it is a random process. Then next assumption is En has got no relation with xn. En and xn are uncorrelated. Okay. Then the variables which decide En are also uncorrelated. Okay. That means any noise, when it is not correlated by any factor, we call it a white noise. So, for example, a very good example will be you measure the voltage of a node in a circuit, or maybe this supply voltage, all right. You keep measuring, you will find it is supposed to be 220, sometimes at this moment it may be 219, next moment it may be 220.5. So, it keeps on changing, fluctuating around that value 220, okay. And how much is that fluctuation? That is unpredictable. There can be an electromagnetic noise outside, there may be a loose connection somewhere, somebody may be switching on or off some load. So, that may cause some line disturbance. So, that is an aggregate of various factors, all right, various uncertain factors, and that variation can be taken as, that noise can be taken as a white noise. So, En is a white noise. A white noise means it has all possible frequency components, all right. Then probability distribution of the error process is uniform. That means the error can occur, say this is from minus delta by 2 to plus delta by 2 with uniform probability. It may be anywhere with equal uncertainty. So, this will be the only exception is for a signal like a step function. If x n is step or x t is a step function, then you have you do not have this kind of an error. If the signal is very complicated, like a speech signal or music signal, where you have large variation in the and very frequent variations, all right, this kind of error modeling will be very accurate. For small values of delta, the uniform distribution, it will be more close to a uniform distribution. This is the probability, this will be of height 1 by delta, total probability is 1. Okay. So, this is the probability density function. Okay. If you go for, instead of truncation, if you go for a rounding off, then error is always negative. Okay. 5.356, I round it off to, sorry, it's the other way around. Truncation, it will be always negative. It's a rounding off, error is always negative between minus delta and 0. Think over this. Think over this. Yes, for rounding off it will be minus delta to 0. Okay. So, from here sigma e squared will be delta squared by 12. You take the square of the error, all right, integrate and then find out from there. Sigma e squared is 2 to the power minus 2b into xm square divided by 12. Okay. So, signal to noise ratio SNR, which is defined as sigma x squared, variance of the signal divided by variance of the error is 10 log of, substitute for sigma e square this quantity. So, it will be 12 into 2 to the power 2b into sigma x squared divided by xm squared. Okay. So, that gives me 6.02b plus 10.8 minus 20 log of xm by sigma x square. I have taken that 2 on this side, so that has become 20, and I have just inverted it, so it has become minus. All right. Now, if you see from here, signal to noise ratio, if it is high, that means the noise component is very much reduced, and it will be high if I increase 1 bit more. If I have the representation 1 bit more, I gain by 6 dB almost. Okay. So, if B is high, SNR goes up. All right. That means the noise component reduces by 6 dB per bit, and this tends to, okay, this term minus 20 log of xm by sigma x. For a sinusoid, xm by sigma x, at the most this will be x peak by root 2, is it not? The variance for a sinusoid, you can see variance for a sinusoid is, it is a zero mean process. So, its RMS value is basically giving you variance. So, it is xp by root 2. All right. So, if you restrict xp, if you take a very small sinusoid, then this quantity will be large. All right. So, SNR ratio will be small. That means, if you take a very small signal compared to the available range, then you are likely to have a very poor SNR. All right. So, and if you exceed it, if you take a very large quantity, very large value of xp, then there will be chopping. Okay. Then also you suffer a lot. So, when you are going for A to D conversion, you must be careful. You should choose the scale such that it matches with the range available. Okay. For again signals like speech signal or music signal, the variation is very large and the amplitude is always centered around the 0 value. Okay. It changes on both sides. So, for speech and music signals, now it can be shown, it tends to be a normal distribution. Okay. It tends to be a normal distribution. In a normal distribution, if I take 4 times sigma x, if sigma x is the variance, 4 times this, then what percentage of the points will be lying above this or below this? It is about 0.064%, very, very small fraction. All right. Actually, 3 sigma covers almost 99, more than 99%, all right. So 0.064% above 4 sigma. So practically no signal is present here. If you adjust, therefore if you adjust sigma x to xm by 4, if you adjust sigma x to xm by 4, then SNR will be 6 b, b means that bit length minus 1 minus 1.25 dB. Okay. So that is coming from here. Xm by sigma x is 4, so 20 log of 4, okay, log of 4 is 0.6, so 20 to 0.6, 12, so minus 10.8 minus approximately 12, that gives me this, all right. So this is all about a very brief description about the error that we come across in quantization, and we have already discussed about the quantization of parameters. In the next class we will take up some examples. Okay. Thank you very much.